We're doing root locus by hand, and we already went through step 0 and rules 1 through 3. I'll quickly review that. For this example, step 0 was just merely plotting the poles and zeros of this L. And here they are for this example. And remember, okay, these X's are the poles of L, and they're the starting points of the poles of the whole closed loop system. And in fact, we call where the poles of the closed loop system go, we call them branches. There's as many branches as there are these X's, as there are poles of L. So the poles of the closed loop system start at these X's. Where would they end up? Well, they'll end up at the zeros. But if you have more poles than zeros, we call the other zeros zeros at infinity. So they'll go off the chart somewhere. In this case, the other two branches. Where are the root loci on the real line? To know that, you can ignore complex poles and zeros. Just look for poles and zeros along the real line. And where you have an odd number to your right, that's where the root loci branches are on the real line. So start over here, no poles are 0, 0. Here you hit 1. 1 is an odd number. Keep going left, ignore complex poles. Here you hit a 0. Now the number is 2. So to the left of that, nothing on the real line. Here's where the root loci are on the real line. And where do the asymptotes go? Well, there are going to be as many asymptotes as whatever n minus m is. In our example, we had 3 poles and 1 0, so the difference is 2. So we're going to have 2 asymptotes in that case, straight up and straight down. Here's the pictures. We always have equal angles. Here it is, I guess, 180. Here it's 120. Here it's 90, etc. This is the kind of stuff I let my students put on a formula sheet. Here was another formula to put on your formula sheet. It said, where is the center of those asymptotes, which will always be on the real line. Here we did that calculation. It was here at 3/2. We're going to have 3 poles starting at these X's. 1 will end up at this 0, and the other 2 will go off straight up and straight down along this dotted line. I mean, it will asymptotically approach that dotted line, ultimately going straight up and straight down in the limit. Okay, now we get to a new rule, rule 4. Where we're looking for branches are going to come out of these X's, right? At what angle do they depart these X's, these poles? The angle is measured zeros from horizontal right, counterclockwise. Here is 0, straight up is 90, left is 180, etc. We want to calculate what angle it comes out of the poles. Well, for simple poles, meaning not repeated poles, let's say we pick pole 1, we do this 1 pole at a time. It's the sum of the angles from the zeros to that pole minus the sum of the angles from the other poles to that pole minus 180 degrees. So these are the angles from the other pole to the pole in question. And a lot of times we can do this by eyeball. I'll show you the exact way to do it, but a lot of times by eyeball is good enough. And I'm going to say any pole that's on the real axis, the angle of departure is going to be either straight right or straight left. Let's look at this pole up here. Let's see. First, some of the angles from the zeros. Here's a 0. What's this angle? I'll say it's about 70 degrees. Now, we're looking at this pole again. What are the angles from this pole and from this pole? Well, this one, it's easy. It's 90 degrees. There's no fuzz on that one. On this one, go around, it's past 90. I'll say it's about 120. And we subtract 180. If I do all that arithmetic, I get minus 320. I can always add or subtract 360. I get a plus 40 degrees for the departure angle out of this pole. Let's say it's about like this. So the branch coming out of this pole is about like that, about 40 degrees angle. The root locus is always symmetric about the real axis. So I know this guy is going to come off at like minus 40 degrees. If I had to do that exactly, I need to take inverse tangents. Let's see, this guy is going to be, oh yeah, he's imaginary part over the real part. He's 4 above. This guy, this pole is at minus 3 plus J4. So 4 units above the real axis, 1 unit to the right. Inverse tangent of 4 over 1. Let's see, this guy's, it's 8 over 0. As long as it's over 0, you know it's going to be 90 degrees. This guy's going to be what? Plus 4, but a minus 2. Minus 1 to minus 3. You have to do those inverse tangent calculations. You do them correctly on your calculator, you get 49 degrees. Instead of by eyeball, we get 40 degrees. Yeah, be careful with that inverse tangent on your calculator because it really requires 2 arguments. So when you have these things over 90 degrees, you got to be careful. Yeah, if you do the same calculation for the other 2 guys, well, this guy, you can just use symmetry. And if you do it for this guy, it's going to say just go straight left. Yeah, and if you're looking at a pole on the real line, complex pairs are going to cancel, so you don't even have to worry about them. And in this case, the angle from the 0 to that pole is 0, so you just get everything 0 except for minus 180 in the formula at the end. That's or zeros. I call them arrival angles. But for any 0, there's going to be like, think of a little line coming out of that 0. Come straight out to the right. That's the departure angle. But then the branch will be coming in to the 0 from along that line. Here's the formula for a simple 0. Looking at a 0, add the angles from the poles, subtract angles from the other zeros, and add 180 degrees. In our example, let's see. Complex pair is going to cancel. The angle from this pole to that 0 is 180 degrees. There are no other zeros, so that's a 0. And add the 180. 180 and 180 is 360, which is the same as 0. So see think of a line coming out of this 0 at the angle of 0, and it's along here to the right. But the root locus is going to be coming into the 0 along that line. Kind of funny that you call that an angle of arrival. That's the way it's calculated. Where do we stand? Well, I'll say it's, if you have repeated poles and zeros, it's a slightly more complicated formula. put this on your formula sheet. I'll do an example where this happens. I'll do an example later. Here's some labor saving tips. You can ignore complex pairs because they're going to cancel. If you're looking at a real polar zero, ignore complex pairs because they're going to cancel. You could ignore poles and zeros to the left because those angles are going to be zero. And you can ignore if you have a pole and a zero on the same side, you can ignore them because they're going to cancel each other. So here's where we stand after applying rules 1 through 4. Branches are going to come out of these X's. This guy starts out straight left, and it's going to end up straight into this 0. These guys start kind of up and kind of down, and they ultimately asymptotically approach asymptotes. You could think of as the poles repel the branches, and zeros and asymptotes attract the branches. Sometimes it's not always obvious exactly where they go, but they don't do crazy things. It's always symmetric about the real axis. And often these first 4 rules are enough to do a rough sketch of the root locus. And you can even calculate those departure angles by eyeball if it's close enough. This is kind of actually the end state. We could stop there and say that's close enough. And I'll do more rules in future videos.